Everyone, and welcome to the first session of POPL this year in 2008. Okay, everyone, welcome to the first session of POPL, where we combine two of our favorite things, types and effects. And the first talk today is going to be a talk on adding linear types to Haskell by Arnaud Spiwack. And welcome.
Thank you, and thank you everybody for being here. I'm Arnaud from Tweag. And I can hardly believe I'm here. At least two years ago, me can hardly believe he's here. Let me explain. So this all started, we were working on a distributed storage project. And probably because we were biased, the idea of linear types came up from time to time, until it became a joke. Every other week, it was like, you know what would be helpful for that? Linear types. So after joking about that for, 6 months, we decided we could actually take the joke seriously. So the idea of using linear types to solve programming problems is not new, at all. And since the 80s, when linear logic was introduced, it has been immediately picked up by computer scientists. And you can see the 1990 paper from Phil Wadler. I don't know if you can read the date, but it is early enough. It was before Haskell, and that had been suggested as a way to deal with effects before we discovered the idea of monad. So it's really not something new. But on the other hand, nobody does it. So why is it? The reason is that there doesn't seem to be a very good way to introduce linear types in a way that doesn't mess up the rest of the language. It changes things. And Rust is a good example of that. It's a wonderful language that embraces linear and substructural logics at heart, but then it is designed around this. And so you get something like this. This is not Rust. This is like a pidgin Haskell written using an interstitial linear logic language. And everything seems to be needs to be annotated and deboxed whenever you're using something. There has been other ways to do that, but so far they only created fairly complex systems, and they're completely fine. They're really nice systems that work quite well, and you can program normally in them and linearly in them. The problem is that when interacting with a full-blown programming language, like Haskell in our case, or OCaml, or something else, then all these complex features, it's not clear where they fit. And so that's why 1-2 years ago, if someone told me, oh, you're going to go to a conference in 2 years, and you're going to talk about adding linear types to Haskell, I would say, no way, it happens in 20 years. But it turns out Jean-Philippe Bernardy, who was one of the pictures at the beginning, came up with fairly strong ideas, and he convinced me this could be done, and we started doing this. And what we came up with is something like that. It's about as simple as what I wrote on this slide. Of course, you can see that there's more than 10 extra slides, so I'm lying slightly. But generally speaking, we add one type to Haskell, and it's mostly orthogonal to all the other features, so it's fairly easy to formalize, it's fairly easy to implement. And that's the goal. So what does this type mean? I have to be clear on the fact that if you look at substructural system or linear systems in the wild, they mean vastly different things by a linear function. So I want to be very, very clear on what is the meaning that I intend. And as I wrote there, I say a linear function from A to B is a function that if its result is consumed exactly once, then its argument is also consumed exactly once. And that is the one promise we're making, and this is what we're typing. And what does consume exactly once mean? Well, if you see your data as a tree, it basically means walking through every node once. So for instance, a pair, you would pattern match on the pair and consume exactly once both of the components as part of your evaluation of your program. And to walk you through the implications of this, I will walk through one example for the rest of this talk. And this is mutable arrays. So this is how we do mutable arrays in Haskell. Actually, this is how we do immutable arrays in Haskell, but we use mutable arrays to implement them. So let's look at this. We take a list, an association list that represents the array, but as a data type. And then we allocate a new array, it's mutable, and we go through the list and write all the cells the way they should be, and then we freeze the array. And that's where the real trick is. So we don't change the array, we just return this array with the promise that we will never, ever mutate it again. And of course this isn't safe, because the language cannot check that. I could have snuck out, a mutable array and then mutate it, and then suddenly I have this array that promises to be immutable, and that breaks referential transparency, and that is bad, and that breaks Haskell, and you might get segfaults and things like that. Really bad. So, of course, it's a bit of a toy example, but what I want to walk you through is how can we use linear types to make freeze safe. So it looks a bit like this. The structure of the code is a bit different. We have a fold instead of a forem, but that's pretty much the same thing. So the same components are there. We allocate an array. We go through the list, writing new values in the array, and then freeze. Now, it's safe, because basically I have arranged my API so that the mutable array cannot be referred to after freeze at all. It would be a type error. So how do we do this? Let me take you through the moving bits. So let's start with read, which I don't actually use, but it's a good example. So let's look at this type very closely. It takes an array, it returns an array. Why is that? Because we will arrange that every function that uses arrays will make this array disappear so that no one can use them. But read, it says, okay, I can mutate an array. After I read it, I can still mutate this array. So I will return it as well. But it's the same array. And we return an A. That's the value we read, the element of the array that we looked at. And almost, because what I said is, if I consume the pair exactly once, then I consume the array exactly once. Consuming the array exactly once is my goal. This is what I must do. So I must consume the pair exactly once, which means, as I said earlier, consuming both components exactly once. And the second component is the element I want to read, and I don't really care about reading it exactly once. So it's not exactly what I want. That would be really painful to use. So let me introduce a new data type. I read it unrestricted, and I write it U because I'm lazy and because slide space is precious. So it's just an ordinary data type, but it's in its type that it's storing something that is nonlinear. So when you pattern match on it, what you get out, the end in the orange square, is unrestricted, and you can use it as many times as you want. And that doesn't violate the linearity constraint. So that's much better. We have a bit more of a syntactic overhead, but apart from that, this is exactly what we want as a semantics. So that's it for read, but let's look at the difficult bit. That's the new array. So how do we do this? Okay, so we could try doing something like this, but this is really, 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 really not what we want. Because this is a linear function, and it says, if I consume the array exactly once, then I consume the integer exactly once. And there is nothing right about this. It means that I can use the array as many times as I want, just if I use it exactly once. If I consume it exactly once, then it means something for the integer. And I don't care about the integer. I can use it as many times as I want. That's really not my semantics. And the problem here is that linearity is a property of functions, so we have to take a function and say, to define a consumer, and say that the array is consumed by this function. So basically, we say that we want that the continuation consume the array exactly once. We reify this continuation as a function. So that's basic CPS. And that doesn't work. That doesn't work because I can just pass the identity and let the array escape the scope. So the continuation is not airtight, and it doesn't guarantee that it will consume the array exactly once. So we need another trick. Actually, the same trick. It's unrestricted, the U type. So instead of returning a B, of an arbitrary B, we return an unrestricted B. And so we can think of that as, since it's unrestricted, it cannot contain an array. Since arrays have to be consumed exactly once, they cannot be passed to unrestricted. So we have to be a bit careful about that, especially in the context of Haskell, because of lazy thunks, and the lazy thunk could encapsulate the array. But we can make that precise. And if we define, I think we do define, and that works operationally, unrestricted, when consuming a value at type unrestricted of A, to mean just pattern match on it, and exactly once. And the value that we get back, we don't care. And so just to define the function new array, we pattern match on the U of B. So that means, by definition of a linear function, we consume the array exactly once. And that's it. Everything falls into place. We cannot use the array incorrectly, and freeze becomes safe. So, I don't know, victory dance, something. So yeah, that was the idea. Now, let's look at fold, because that was the sort of the last piece. It has a weird type to cope with linear types, and that would be terrible. We don't want to define everything twice or maybe more. It would not be reasonable. It would just, no one would work with that. So our solution is just polymorphism, like standard ML-like polymorphism. Except instead of doing it on types, we do that on linearity. So we have these more annotations on arrows, and the two arrows that we've defined or used so far are just aliases for arrows with indices at a particular value. And we call these values multiplicities, and they can be variables. And suddenly we can have a polymorphic fold-L that instantiates to the normal type of fold-L and the type that we needed. That's much better. So that's pretty much what the system looks like. And so let me take the remainder of my talk to discuss what we've actually done with this. We're pretty serious about this. It's being implemented. But by the way, all the things in this slide are clickable, and I'll put the slides online very soon, so you'll find them in the program. So it is being implemented as a GHC extension, a bona fide GHC extension. It is not something that lives on its own, so it's a good test that it's working. Well, sort of, soon. Be patient or be brave if you want to use it. You can use it today if you will, but it still has bugs, and it doesn't implement the entire proposal. But it is being proposed for inclusion into mainline GHC, and we've designed quite a few examples on it. The first one is in the paper that's been written by Ryan Newton, who's in the audience, and the idea is to work through to just never deserialize the data structure, or never serialize them, and work directly on their serialized form. It's a lot of fun, and it prevents many allocations which can be problematic in a distributed program. The sort of things you just cannot do in a regular type system. It's just so error prone that no one would do that. And my proof is that no one does that. But On the other hand, with linear types, it has been a breeze. It's even fun to do. So that's a good slogan for all of us. It's just linear types are fun to use. And so I've been developing a small libraries for use with linear types to help bootstrap the programs. It has it has an implementation of the IO monad where you can ensure that you never use or free a file that has already been freed or other resources like that. There's a prototype based on sockets as well, where you just cannot use sockets have a very intricate protocol depending on whether they are TCP sockets and UDP sockets, and you have to do these things in order. And so this just guarantees that you use the right steps. I also implemented a version of data types that lives outside the GC heap and that you manually malloc and free, and that is entirely safe. So that's something interesting. We had a summer of code on the streaming library for Haskell, which is a library that looks like it really needs linear types. We've had some success on that. That was, but maybe fine types are better for this. And we have one external contribution, so more victory dances. So Samuel Giannino has implemented a DSL to write 3D models for 3D printers, and these models they are guaranteed not to have wild edges that live without faces attached to them or things like that, which usually in modelization languages are implemented as runtime errors when you evaluate the model. It says things like this model is not water typed. And so by using linear types, he was able to make sure that every model that you write could be printed, and you never get this sort of runtime errors. That's super fun. Just to conclude, nothing that I said is particularly specific to Haskell. There are some complications due to laziness in Haskell that you might not have in a strict language like OCaml, in which case you might be able to do a bit more. Though it's still it's fairly generic, and if you want to add linear types to your language, you might consider giving it a spin. Something I haven't mentioned, but that was written on the slides, is that we reuse the exact same data types as Haskell. So the pairs, what plays the roles of the tensor in linear logic is ordinary pairs, and that is still compatible, and lists are still lists. That's very useful, so that there's a smooth transition with that copying between linear programs and intuitionistic programs. So that ends my presentation, and I'll be taking your questions now. Thank you very much.
I have the mic. Okay, so I have several questions. My first question is about the type you presented for the new array function.
Yeah.
It seems to me that if you use this function as is, well, somehow you invert the control. So this means that you cannot somehow allocate two arrays and deallocate this in a non-nested fashion?
In that case, it's given to the GC, so they can be deallocated in any fashion. But no, the deallocation is not given to the scope. The scope just makes sure that you have deallocated. When you have like the malloc thing that I mentioned, it just tells you have to deallocate before you exit the scope. And so you can be completely non-stack-like.
Yeah, okay, for deallocation, but you have to somehow leave the scope in the same order you created the arrays.
Yes, and they tend to be stuck together at the end. So you have several scope, and they all exit at the same time. It's most common.
Another question I have is, I'm kind of surprised that you decided to introduce linearity by having two kinds of arrows instead of saying that only some types needs to be linear. So does that mean that you have an idea of some example of types that some types are linear and some types are not? There's types that you sometimes want to put before a magic round and sometimes want to put before a normal arrow.
So the goal is explicitly not to do that, and the short reason is it's a trade-off between expressivity and simplicity. You get a much simpler type system, in my opinion, at least something that I know how to implement. Whereas if you take some linear types and you want to have some polymorphism, so you want to have fold being able to handle types of sort linear and of sort nonlinear, you have to jump through many hoops, and this is something that I can do on its own. There are several languages that do that. But I don't really know how to add that to Haskell and all the interaction that it would have with the rest of the system. Because what I didn't try is just implement both solutions and see which one is actually best. So it's mostly a hunch.
What I mean is, yeah.
Yeah, we can take that offline, and I can answer for half an hour if you wish.
Please tell us about error messages. So there was a notorious version of GHC that would delete your source code if it found a type error. I imagine you've probably found a slightly friendlier approach, but how comprehensible are your messages when you make a mistake?
So there is still work to do at this point. What they say is at the location of a binder that introduce a linear variable, for instance, and you have used it non-linearly, it will tell you you've used it non-linearly, and that is bad. The problem is not always completely trivial to understand why this has been computed, because maybe you think you've used it linearly, but it's something else that has the wrong type annotation or something. And what I want to add is just a trace of the calculation, so that we can see why it has been computed as having been used in a more liberal fashion than linear. So far, it's pretty okay, but there's still improvement to be done.
Okay, we have time for one more question.
So I wanted to ask a question about the unrestricted data type you have. It's a pretty cool trick, but it does seem to come at a downside that you have to have an indirection in order to make something unrestricted. So what I was curious about is it possible to replace data with new type and unrestricted and achieve the same thing?
No.
Really?
This would be incorrect, because the strictness of the pattern matching is essential. And if you start using new type for this, the pattern matching will be implemented as identity, which is non-strict, and the linear things that are in your lazy thunk will stay there and will be executed out of order and break. But it's just, for instance, in the case of the malloc thing, it would just segfault. Well, you get memory corruption thing, and it doesn't work. But what you could do is you could have a strict wrapper of a different sort. So Haskell has these strict tuples. You could use a strict one tuple that happens to capture something like that non-linearly, and that would work. I think I haven't done the math yet, and that doesn't cost anything.
Interesting. Thank you.
We have time for one last quick question.
I'll try to have a quick answer.
Yeah, I just wanted to hear if you can tell us something about the multiplicities. Is that you showed 1 and infinity, but is there 0, 1, 2, 3?
In the current formalism, there are just 2, 1 and omega. Mm-hmm. In the implementation, there is a 0 as well, which is super useful for inference. But that could be much more. The relevant literature for that is the co-effect literature. And basically what you need is a lattice-ordered, joint semi-lattice-ordered semi-ring. And pretty much any one of them will do.